Hey everybody, and welcome to what will probably be our last Cal 1 lecture. That we have a very important function to work with today, and it's a function that we'll see quite a bit if we go into Calculus 2. And to set the stage for introducing this new function, let's just take a look at the derivatives of some well-known functions. The derivative of 1/3 x cubed, let's see, 3 times a third is 1. Subtract 1 from the exponent, we get x squared. The derivative of 1/2 x squared, 2 times a half is 1. Subtract 1 from the exponent, we get x to the first. Compute the derivative of x to the first, we get 1 times x to the 0, which is 1. Compute the derivative of x to the 0, but that's just 1. Derivative of 1, derivative of x to the 0, same thing. We get 0 times x to the -1 by the power rule, and that's 0. The derivative of negative x to the -1, let's see, -1 times -1 is +1. Subtract 1 from the exponent, -2. So derivative of negative x to the -1 is x to the -2. The derivative of -1/2 x to the -2, bring the exponent down front. -2 times -1/2 is +1. So we have +1 times x to the power of -2 minus 1. Derivative of -1/2 x to the -2 is x to the -3. And so on and so forth. So on the right side of the equal sign, we have derivatives of functions. On the left side of the derivative of the equal sign, we have the functions that we're computing the derivative of. And notice that nowhere on the right-hand side, let's see, x squared, x to the first, x to the 0, 0, x to the -2, x to the -3. See, nowhere over here do we have x to the -1. Now, if we compute x to the 0, we get 0 times x to the -1, but that's just 0. And no constant that we put out front here is going to change this derivative from being 0. And to get x to the -1, we've run through all of the usual suspects. That we've computed the derivatives of all powers of x for exponents that are near 0. We've computed the derivative of x to all whole number powers that are close to 0. And we never got x to the negative first. And that's significant for a few reasons. One, if you think about it, we haven't seen a function that we can compute the derivative of and get x to the -1. If there is such a function, we haven't seen it. And this also explains why the power rule for integrals doesn't work for the exponent of -1. Think about it. The power rule for integrals or antiderivatives, add 1 to the exponent, divide by the new exponent. This is the power rule for integrals or antiderivatives. But there's a disclaimer here, isn't there? Here's the disclaimer. And we have to add this disclaimer for obvious reasons. If the exponent is -1, and we plug -1 into this formula, guess what? We end up dividing by -1 plus 1. We end up dividing by 0. So when n equals -1, this expression is undefined. The power rule does not give us the antiderivative of x to the -1, which means that we don't know of a function yet whose derivative is x to the -1. That we have not encountered it until now. There actually is such a function, but we have not seen it in this class. If we've seen it at all, we might have seen it in pre-calculus algebra. But we have not seen the function in this class whose derivative is x to the -1. Until now. Ta-da! Here it is. The natural logarithm function. The natural logarithm of x, denoted this way, ln of x, is the function having the property that its derivative with respect to x is x to the -1st power. Or equivalently, its derivative with respect to x is 1 over x. And I'll tell you something. Oftentimes we use this particular form, but both forms are proper. Now I do want to comment on how we refer to this function. Typically we refer to this function as natural logarithm of x, or the natural log of x for short. And there's sort of an easy way to remember this. We can say that the n and the l in reverse order stand for natural logarithm. So when we see this ln, we can just think of the n first and say natural logarithm of x, or a natural log of x. Before we consider further the calculus properties of this function, natural logarithm of x, we should look at some numeric properties and some algebraic properties. And that's what we're going to do next. Oh, by the way, this is not a function that's going to come and go. This is not a function that's of passing curiosity but not of lasting significance. This function, the natural logarithm function, is one of the most important functions in mathematics and science. And the only reason that we haven't seen it yet is because we haven't gotten deep enough into math and science to see it. But this function is at least every bit as important as the trigonometric functions, perhaps even more important. So as we get deeper into science and mathematics, and when I say science, that includes physics, that includes engineering, that includes chemistry, that includes biology, believe it or not, this function turns out to be important. This function and its inverse are very prominent in modeling predator-prey models in biology and ecosystems. This function and its counterpart are very important in creating models that maybe predict the rate of growth of a bacteria colony or the spread of a disease. So you people who are going into biology, don't think you're going to escape this by going into what some people might consider a less mathematical science. Biology, with the passing of time, gets more and more mathematical. And you will see this. This is a very significant function. So before we even consider the calculus properties, we are going to consider the numeric properties and the algebraic properties. Okay, numerical properties of the natural logarithm function. And I will say this starting off. This is one of those functions whose graph we should probably know. Especially if we're going to stay in math and science. If we're going to Cal 2, we should know this graph. If we're going into physics, chemistry, engineering, even biology, we should know this graph. And I'll tell you a story. And you're saying, oh, for crying out loud, another one of his stories. But there is a point to this. When I was in Cal 2, I had to work an exercise that required me to compute the limit of that. I don't like the way this looks. It required me to compute the limit of the natural logarithm of x as x approached 0. And I couldn't do the exercise because I didn't know what this limit was. And it's not like a polynomial where you can just plug in the number and out pops the limit. It wasn't like that. And I thought, well, I can't factor this thing. I don't know. What's the limit? And my best friend's father was a professor in the physics department. And I thought, I know, I'll go ask him. And I asked him, I said, what's the limit of the natural log of x as x goes to 0? And he said, well, I guess that all depends on your definition of limit. And I looked at him and I said, okay, thanks. What? Well, that didn't help very much. Although in a way he was justified to say that. Maybe before we get too far, I'll explain why. But later that day, as a matter of fact, it was about 8 o'clock at night, and I had hung up my studying for the day. I was in a bar with a couple of friends. Now, I was in Cal 2, but I was, 26 years old maybe. I was a late bloomer. And I was with two of my friends who were graduate students in electrical engineering. And I thought, I'll ask them. They'll probably know. They're both really smart. And we had a couple of pitchers of beer on the table, and I asked the question. And neither of them said anything. But one of them pulled the pitcher of beer to his left, and I was sitting to his right. He pulled the pitcher of beer to his left. And in the condensation that was on the side of the pitcher, he drew a graph of the natural log function. And I looked at it and I said, oh, okay. And looking at the graph of the natural log function, even one that's drawn on the side of a pitcher of beer, this picture explained everything to me. And we'll see why in just a minute. But the point is, sometimes if we memorize the graph of a function, that knowledge can take us a long, long way. So let's look and see what we can deduce here. First of all, for what values of x is the natural log of x positive? Well, from recent lectures, we know that when a function's positive, its graph lies above the x-axis. And here, the graph of the natural logarithm function lies above the x-axis for all values of x that are to the right of this point. In other words, for all values of x that are greater than 1. So, thanks to the fact that we know what that graph looks like, we know that the natural logarithm of x is positive whenever x is greater than 1, and vice versa. Now, for what values of x is the natural logarithm function 0? Well, when the natural logarithm function is 0, that means that y is 0. So when the natural logarithm function is 0, that's where the graph crosses the x-axis. Right at this point, x equals 1, y equals 0. So when x equals 1, the natural logarithm is 0, and vice versa. If the natural logarithm is 0, that means that x equals 1. Now, for what values of x is the natural log of x negative? And a function is negative wherever its graph drops below the x-axis. And that's to the left of x equal negative 1. So in other words, when x is less than negative 1, when x is less than 1. But we're going to have to watch it. Look at this graph. And does the graph of the natural log of x cross the y-axis and come to the other side? It doesn't. The graph of the natural log of x lies completely to the right of the y-axis. In fact, the graph of the natural log of x never even touches the y-axis. This is the one function in mathematics where we have a vertical asymptote, and yet there's no algebraic division by 0. Tangent, cotangent, secant, cosecant, they all have vertical asymptotes. But if we analyze what the functions are in terms of sine and cosine, we can see, okay, tangent, cotangent, secant, cosecant, they have vertical asymptotes wherever the denominator is 0. The natural logarithm function isn't like that. We can't write this as a denominator beneath a numerator. This is the one function that has a vertical asymptote, yet there's no division by 0. That's why when we were doing vertical asymptotes, we said, okay, if we want to find the vertical asymptotes, find the x values that cause division by 0, and there are candidates. Because if we have a vertical asymptote, we're dividing by 0 there. And that's true of every single function except the natural log function. This is the only function where that isn't true. So, this graph never even touches the y-axis, which means that when x is 0, there's no point on this graph. So more precisely, we can say that the natural log of x is less than 0 for x between 0 and 1, not inclusive. Now, if we plug negative 1 in here, or if we plug 0 in here, what's going to happen? If we're using a calculator, our calculator will start to smoke after a couple of seconds, and then it will burst into flames, and then we're going to have to get another calculator. The natural log of x is undefined for x less than or equal to 0. Yeah, don't plug 0 into a natural log function. because if you do, terrible things will happen. The entire Earth and even this whole solar system and the sun will get sucked into a giant black hole and will never be heard from again. That'll be the end of all life on Earth and the end of all planets and stars surrounding us. So don't ever plug 0 into a natural logarithm function. Don't plug a negative number into a natural logarithm function. Bad things will happen. And I don't think it will really be the case that the Earth will get sucked into a black hole if we plug a negative number in here, but why risk it? It is the case that our calculator will start smoking and it will burn up and we'll have to buy another one. So don't plug a 0 or a negative number in here. We'll save ourselves some money on a new calculator. Now, the question that I wanted an answer to decades ago, the limit of the natural logarithm of x as x approaches 0 from the right. So if we move in this direction, x is approaching 0 from the right. And if I move along the graph in this direction, I'm moving along the graph in such a way that x is approaching 0 from the right. And as x approaches 0 from the right, what happens to the natural logarithm of x, the y value? Huh? It goes straight down to negative infinity, doesn't it? And we can tell that just by knowing what the graph of the natural logarithm function looks like. As x approaches 0 from the right, natural logarithm goes to negative infinity. Now, why did my best friend's father say, well, that all depends on what you mean by limit? Well, see, when we say limit, we're talking about x approaching a certain value from either direction. And with the natural logarithm function, if x approaches 0 from the left, f of x, the natural logarithm of x, isn't approaching anything because it's not defined over here. So the limit as x approaches 0 from the left of this function just doesn't exist. Because if x approaches 0 from the left, we're in a region where this function isn't even defined. So of course the limit can't exist. And my best friend's father was justified in saying what he said. It didn't help me very much, although in retrospect, maybe he was implying that I was asking a question that I should already know the answer to. But years later, I appreciate his answer, and I know what he meant by it, even though at the time I didn't. Now, from looking at the graph, we know what the limit of natural log of x is. As x approaches 0 from the right, it's negative infinity. The graph tells us that picture. And when I was a student in Cal 2, this graph on the side of a pitcher of beer gave me this answer. Knowing what the graph of a function looks like is very important. Especially the natural logarithm function. Now, we're going to use this graph to answer one more question. What is the limit of the natural logarithm of x as x approaches positive infinity? So if x approaches positive infinity, x is moving this way. And if we move along the graph in such a way that x approaches positive infinity, natural log of x, the y value, goes to, and this is subtle, x is approaching positive infinity. And the graph keeps increasing. And we wonder, well, you know, the graph is increasing. Does it really go to positive infinity? And the fact of the matter is, it's not obvious that it does. It's obvious that it might go to positive infinity as x goes to positive infinity, but we're not really sure looking at the graph. But the answer is yes. As x goes to positive infinity, the natural log of x goes to positive infinity also. It's just that the graph takes its sweet time getting there as x approaches positive infinity. As x approaches positive infinity, natural log of x goes to positive infinity, but it takes its time getting there. Now that we know that, as long as we know what the graph of natural log of x looks like, we'll know what this limit is. We'll say, oh, as x goes to infinity, oh yeah, positive infinity. So these are the numeric properties of the natural logarithm. And knowing what the graph looks like is a wonderful thing, because we should probably look at this graph and correlate all of these properties with what we see on the graph and vice versa. Knowing the graph of a function, especially this function, is worth quite a bit. Now, we've looked at numerical properties of the natural logarithm. We also need to look at algebraic properties of the natural logarithm. So that's what we're going to do next. Natural logarithm algebraic properties. And here they are. Number one, this is the fundamental property that all logarithms have. And properties 2 and 3 pretty much spring from property 1. But a logarithm is a function that converts multiplication into addition in this manner. The logarithm of a product is the sum of the individual logarithms. That's the fundamental property that all logarithms have. And think about analogies. Multiplication is to division as addition is to subtraction. So a natural logarithm, or a logarithm of a quotient, is the difference of the two logarithms. Logarithm of the numerator minus logarithm of the denominator. And then finally, a logarithm transforms exponentiation into multiplication in this manner. We take the exponent of the argument of the natural logarithm function and bring it outside as a multiplier. And this looks very reminiscent of the power rule for derivatives, but it's not. So I'll write a note. This is not a derivative. We are not computing a derivative here. And we have to remind ourselves this is an algebraic property. We look at this, and the easiest thing in the world is, okay, bring the exponent down front. And before you know it, we're going to start thinking derivative. But this has nothing to do with derivatives. This is strictly an algebraic property. So we've seen the fundamental properties of natural logarithms. Let's do some exercises that will force us to use these algebraic properties. Here are a number of great algebraic properties to work on for natural logarithms. The natural logarithm of 12. Now we're told approximate the value of these things using only the facts that the natural logarithm of 4 is approximately 1.4 and the natural logarithm of 3 is approximately 1.1. So, how are we going to do this? The natural logarithm of 12. And here's the key. If we have any chance at all of doing it, it's going to hinge upon our ability to relate 12 to 4 and 3, because we know what the natural logarithms of 4 and 3 are. We don't know the natural logs of any other number. So we have to write this number in terms of 4 and 3. So natural logarithm of 4 times 3, right? Or 3 times 4. Natural logarithm of 3 times 4. And now we can use property 1, which says that the logarithm of a product is equal to the sum of the two logarithms. So natural logarithm of 3 plus natural logarithm of 4. And this is exactly where we want to be because we know what each of these things is equal to approximately. Natural logarithm of 3 is approximately 1.1. Natural logarithm of 4 is approximately 1.4. So we get 2.5. Now, oh, by the way, let me document this. Property 1. Just in case you're wondering where this came from, property 1. Okay. So I guess I'm going to have to move all of these guys down a little bit if I'm going to document my work like this. 2, natural logarithm of 4/3. How are we going to compute this? Well, we won't unless we can rewrite this in terms of things that we know, namely 4 and 3. Oh, well, it is in terms of things we know, isn't it? We know the natural logarithm of 4. We know the natural logarithm of 3. And this is the logarithm of a quotient. So which one of these properties are we going to use? Property 2, right? Which says the logarithm of a quotient equals the difference of the natural logs. So this is going to be natural logarithm of 4 minus natural logarithm of 3 and I might as well write property 2 here. And we know what these guys are approximately equal to, 1.4 and 1.1. So the natural logarithm of 4/3 is approximately 0.3. And if you check this out on the calculator, it'll be darn close. It may say 0.298 or something like that, but it's going to be really close. Now, the next one, natural logarithm of 3/4. This is written in terms of things we know already. We know the logarithm of 3. We know the natural logarithm of 4. And we have the logarithm of a quotient. So again, we're going to use property number 2, which tells us that the logarithm of a quotient equals the difference of the natural logs. So natural log of 3 minus the natural log of 4. And again, we'll note that this is property 2, which talks about the logarithm of a quotient. Okay, logarithm of 3, we know what that is. Logarithm of 4, we know what that is. 1.1 minus 1.4, which is negative 0.3. Now let's just stop for a minute and take a look at our answers, just so that we can tie this in with something else that we already know. 4/3, that number is greater than x. And notice that it's 4/3, it's greater than x, and its logarithm is positive. Did I say that right? 4/3 is greater than 1, and its logarithm is positive. 3/4 is less than 1, and its logarithm is negative. 12, it's greater than 1, its logarithm is positive. But see, right here we have a number that's just a little bit bigger than 1, and it's a small number, but it's positive. Here we have a number that's just a little bit less than 1. It's a small number, but negative. So again, logarithm of a number bigger than 1, positive. Logarithm of a number less than 1, negative. So it's not a coincidence that this one turned out positive and this one turned out negative. Now, I guess we wanted to do number 4. And I'll tell you what. I'll leave these up here for about 10 seconds just so you can take a longer look. And then I'll erase them and I'll move on to number 4 because I think I want to do it 2 ways. Okay. Natural logarithm of 9. If we have a prayer of computing this, we've got to write it in terms of 4 and 3. And one way that we can do this is to say that 9 is 3 times 3. And then we can use property 1, which tells us how to compute the logarithm of a product. The logarithm of a product is the sum of the 2 logarithms. So that's property 1. And we know what the logarithm of 3 is. It's 1.1. So this is approximately 1.1 plus 1.1, which is 2.2. So the natural logarithm of 9 is approximately 2.2. Let's try this a different way. And I think some of you probably already thought of this. Natural log of 9, we have to write it in terms of 3, but maybe we can write 9 as 3 squared. And then that will allow us to use property 3, which says if we have the logarithm of something raised to a power, we can bring the exponent out front as a multiplier. And it almost looks like the product rule, but it's not. It has nothing to do with derivatives. It is strictly an algebraic property. So this is going to be 2 times the natural logarithm of 3. And this is by property 3. And now we just plug in the approximate value for natural logarithm of 3. 2 times 1.1, which equals 2.2. And if these properties are correct and consistent, then we have to get the same thing both ways, which we do. So it was good to do this both ways just to see that property 1 and property 3 are perfectly consistent with one another. Now, as our last one, let's do number 5, natural logarithm of 2. And again, in order to do this, somehow we have to write it in terms of 4 and 3. And we have to write it in terms of 4 and 3 in such a way that we can write it as the logarithm of the product of two things that we know, or maybe as the logarithm of something we know raised to a power. And I'm going to go with number 3, that property. I'm going to write natural log of 2 is equal to 4 to the 1/2 power, because I know that the square root of 4 is 2, and I know what the logarithm of 4 is. So I took the logarithm of 2 and wrote it in terms of 4, because I know about the logarithm of 4. And property number 3 tells us bring that exponent out front. So we bring the exponent out front as a multiplier. And thus we have property 3 again. And I hope you panicked when I wrote the plus sign here. These two things are equal by property 3. So natural logarithm of 4 to the 1/2 power is equal to 1/2 logarithm of 4. And I'm sorry, I didn't mean to give you a panic attack. We know what logarithm of 4 is. It's 1.4. So the natural logarithm of 2 is approximately equal to 0.7. I have some homework exercises of this fashion that I'll give you to work on after this video. Algebraic properties of logarithms. Right now, we're going to get back to the calculus of natural logarithms, because that's really what got us on this discussion in the first place. We're back. Remember, the derivative of natural log of x is x to the -1. Very often we write it this way without using the negative exponents. Derivative of natural log of x is 1 over x. Well, suppose we have a compound function. Suppose we have a composite function, the natural log function being the outer function, and just some generic function g of x being the inner function. It's a chain rule exercise. And what we're supposed to get, according to the chain rule, let's see, derivative of the outer, evaluated at the inner, times the derivative of the inner. Okay, so we're supposed to get the derivative of the outer, evaluated at the inner, And we're supposed to get times the derivative of the inner. Since we haven't worked with this function before, let's write our scratch work here. And the outer function is the natural logarithm of something. And we need to know the derivative of the outer function. Well, think about this. The derivative of natural log of x is 1 over x. So the derivative of natural log of something is going to be 1 over something. That's the derivative of the natural logarithm of x. This is the derivative of the natural logarithm of something. 1 over something. So the derivative of the outer, 1 over something. And now we have to evaluate it at the inner, g of x. And then we have to multiply by the derivative of the inner, g prime of x. This is the derivative of the natural logarithm function evaluated at some other function. So I will write that a little bit more succinctly now. Here is derivative of the natural logarithm evaluated at a function rewritten. The derivative of the natural logarithm of something is 1 over the inner function times the derivative of the inner function. And that's pretty much how we're going to think of it when we compute derivatives. We're going to compute the derivative of natural logarithms quite often. And essentially when we do that, we're going to say, okay, 1 over the inner times derivative of the inner. That's the way we're going to do it. That's the way everybody who does calculus computes the derivative of the natural logarithm evaluated at a function. 1 over the inner times derivative of the inner. So let's do some examples. Derivative of, natural logarithm of x cubed plus x squared plus x. And here's our inner function. So we expect to get 1 over the inner times derivative of the inner. So let's do it. 1 over the inner function, 1 over x cubed plus x squared plus x. So 1 over the inner times derivative of the inner, 3x squared plus 2x plus 1. And if we leave it like that, that's fine. This is fine. Or if we want, we can just simplify it. 3x squared plus 2x plus 1 over x cubed plus x squared plus x. This is how we compute the derivative of the natural logarithm of something. Let's do a few more. Well, that's not a logarithm problem, is it? Silly me. Okay, there's a logarithm problem. And we're going to get 1 over the inner times derivative of the inner and here this really does need to be simplified because it's pretty simple to simplify. So we'll have 5x to the 4th over x to the 5th. And son of a gun, we can cancel an x to the 4th out of top and bottom. And we just get 5 over x. Wow. Well, let me ask you something. Could we have done that a different way? Maybe. Let's try this thing a different way, just to illustrate the consistency of the algebraic properties of natural log. We have the natural logarithm of x to a power. So before we even compute the derivative, we can use the algebraic property, which says we can bring the exponent down front as a multiplier. So this gives us derivative of 5 times natural log of x. And now this is the derivative of a constant times a function, isn't that right? So what do? We write down the constant, and then we forget about the constant for a while and write the derivative of the function. What's the derivative of natural logarithm of x? 1 over x. Okay. And then we multiply them together. And son of a gun, we get the same thing either way, which we should if these rules are consistent. Now that brings up a point. Sometimes it's a good idea to simplify the expression before we compute the derivative in the case of a natural log. And I'll illustrate that later. Right now, let's do a few more examples of derivative of natural log of x. Oops. So here's the inner function. And we should get 1 over the inner times derivative of the inner. So 1 over the inner function, 1 over sine of x. Derivative of the inner function, cosine of x. And if we were to stop there, that would be fine. But suppose I do simplify this and just multiply these two things together. I'll get cosine of x over sine of x. And boy, that sure looks familiar. Cosine over sine. Oh, it should look familiar. That's cotangent, isn't it? So, you know, maybe this explains why we didn't have an integration formula for cotangent. And we didn't. We had an integration formula for sine and one for cosine. And then we had an integration formula for secant squared x and cosecant squared x. And we had an integration formula for secant x tangent x and cosecant x cotangent x, because we knew the functions that we had to compute the derivatives of to get those things. But we didn't have a derivative, we didn't have an integral or an antiderivative formula for cotangent x, because until just this very minute, we had never seen the function that we had to compute the derivative of to get cotangent x. The function that we compute the derivative of to get cotangent x is natural log of sine of x. So we can say, based on this, and we will address this a little bit later, but we can say the integral of cotangent x dx is natural logarithm of sine x. And the reason we didn't know the antiderivative or the integral of cotangent x before this was because we had never seen this function before. So how would we know what function we have to compute the derivative of to get this thing if we'd never seen that before? See, one more differentiation exercise before we start to get cute. Now, I don't think there's anything profound about this exercise. It's just another exercise that we're going to do for the sake of practice. So here's our inner function. And the derivative of the log evaluated at something is 1 over the inner times the derivative of the inner. So here we go. 1 over the inner function. 1 over sine of x plus x times the derivative of the inner. Okay, cosine of x plus derivative of x is 1. That's the derivative. And we can leave it like this, or we can tidy it up a bit by multiplying these two things together. So now I guess it's time to get cute. It's time to get cute. Well, here's the inner function. So let's see. The derivative of this will be 1 over the inner times the derivative of the inner, and that means we're going to have to use the quotient rule. Ugh. Well, all right. 1 over the inner function. Okay, so that's going to be 1 over x cubed plus x squared plus 5 over x squared plus 2x. So there's 1 over the inner. times the derivative of the inner. Oh, the quotient rule. Well, if we have to use the quotient rule, it's a nice thing to have. But if we don't need to use it, we usually try to avoid using it. Here, derivative of the quotient is top prime, 3x squared plus 2x, times the bottom, x squared plus 2x, minus bottom prime, 2x plus 2, times the top, x cubed plus x squared plus 5, all over the bottom squared, x squared plus 2x squared. Okay, so here's our derivative of the inner. What a pain this was. This is one ugly looking derivative, let me tell you. Sometimes there's a better way. Three exclamation points there. I must really be serious this time. Sometimes we can simplify first using algebraic properties. Okay, I'm game. I sure don't want to have to go through what I went through here anytime soon. Natural logarithm of x cubed plus x squared plus x to the 5th over x squared plus 2x. We have the natural logarithm of a quotient. So we can write this as the natural logarithm of the numerator minus the natural logarithm of the denominator. Guess what? No more quotient, no more quotient rule. This is now the derivative of the difference of two functions. So we compute the derivative of the first, the derivative of the second, and then just combine it. So derivative of the first is 1 over the inner, x cubed plus x squared plus 5, times the derivative of the inner, 3x squared plus 2x, okay, minus the derivative of the second, which is 1 over the inner, 1 over x squared plus 2x, times the derivative of the inner, 2x plus 2. Now I'll tell you what, this was a lot easier than doing it the other way. Sometimes we can simplify first using the algebraic properties of derivatives. And sometimes that makes it easy. If we're computing the derivative of the logarithm of a quotient, we may want to simplify first. Let's look at another situation where we definitely would want to simplify first. This one is truly a horrible exercise. that we have the derivative of a natural logarithm of a quotient, but it's even worse than that. Natural logarithm of square root of x cubed plus x squared plus 5 all over, what, x squared plus 2x, let's say. So we've added the feature of a square root. Well, you know me, one of my favorite words is rewrite. And typically, whenever I see a square root, I'm thinking rewrite for sure. So, first thing, get rid of that radical sign. And instead, I'll write it as something to the 1/2. X cubed plus x squared plus 5 over x squared plus 2x. That whole thing to the 1/2. Okay. Now I got rid of the radical. This still looks pretty sinister. I have the natural logarithm of a quotient raised to a power. So if I leave it like this, I'm going to get 1 over the inner function. And then I'm going to have to use the derivative of a function raised to a power. And then I'm going to have to use the quotient rule. And I'm not a glutton for punishment. I am not doing that again. So I'm going to use my favorite word again. Natural log of something raised to a power, I can bring that exponent out front. I surely can. So I'll have derivative of 1/2 natural log of x cubed plus x squared plus 5 over x squared plus 2x. Well, it's still not simple, but it's simpler than it was. And you know what? I'm on a roll. Why not rewrite it again? The rewriting is simple compared to using the chain rule, the quotient rule. And we're going to have to use the chain rule twice if we leave it in this form. So rewrite again. And I have 1/2 the natural log of garbage. Well, it's the natural logarithm of a quotient. And the natural logarithm of a quotient is the natural log of the numerator minus the natural log of the denominator. So natural log of the numerator, x cubed plus x squared plus 5x, no, just 5, minus natural log of x squared plus 2x. Now it looks incredibly simple, except I didn't put my ddx down here. Now there's one thing I do need to take care of. This 1/2 multiplies the natural logarithm function. So when I compute the derivative of the natural logarithm function, this 1/2 should multiply the entire derivative. And I'm getting ahead of myself. This 1/2 multiplies the entire natural logarithm function. So when I split this logarithm into the difference of two logarithms, this 1/2 should multiply the entire difference of the logarithms. So I need to put this in parentheses here, because this whole thing, logarithm minus logarithm, is this logarithm. and 1/2 multiplies this entire logarithm. So 1/2 better multiply its equivalent, which is the difference of those two logarithms. So I need parentheses around those two. Okay, I got the derivative of a constant times a function. So we write the constant down, and then we do the derivative of the function. And it's easy. Natural log of something. So it's 1 over the inner, x cubed plus x squared plus 5. 1 over the inner times derivative of the inner, 3x squared plus 2x, minus this derivative, 1 over the inner, 1 over x squared plus 2x, times the derivative of the inner, 2x plus 2. This is our entire derivative. Does it look complicated? It is kind of complicated, but I'll tell you what, if we computed the derivative of the function in this form, we probably need about 3 whiteboards this size to work it all out. We definitely took the coward's way out by rewriting it 3 times before we computed the derivative. And no, we're not cowards. We're mathematicians, which means we're smart. We don't do anything the hard way if there's an easy way, because we're smart. You know, we don't say, hey, I dare you, hit my hand. I'm going to trick them. I'm going to move my hand. Well, we don't do that. We're smart. If there's an easy way to do something, we do it the easy way. Not because we're lazy. Well, okay, we're lazy, but we're also smart. And not because we're chickens, but, yeah, well, we are chicken a little bit, but mostly because we're smart. So instead of tackling this monster here, instead of fighting with Godzilla or Tyrannosaurus Rex, we dismembered Tyrannosaurus Rex piece by piece, and then did battle with it. Not because we're cowards. Well, we might be a little bit. Not because we're lazy. Well, we might be a little bit. But primarily because we're smart and we want to do things the easy way instead of doing things the hard way.